All right, ladies and gentlemen, get your notebooks out and let's hit the road running here. I'm going to do a little bit of review just to remind you where we've been so you can see that where we're going. We've already talked about heat flow and the fact that heat can flow from one thing to another and negative Q lost is equal to Q gained. And so this is something we already know to be true. And we've talked about the fact that we can look at that in terms of temperature changes. And we've done problems with Q is equal to SM delta T. And then mentioned the fact that we've got phase changes. And so that's going to be our focus today. The key with a phase change is there's no temperature change. It's simply melting, boiling, freezing, condensing, whatever. And then we also mentioned something coming up later, our chemical reactions. So those are things as well. So one of the points I want to make with you is this is what we've been doing so far, right? You got like certain mass of water, it changes in temperature from one temperature to another, and you figure out what Q is. And this kind of problem is essentially plug and chug. You figure out specific heat, mass, temperature change, you plug it in, you solve for something that's missing. That's where we've been. Now, these next ones that we're looking at, both of these, we're going to be focusing once again back on unit analysis, simple unit analysis, but just so that you're aware of that. So here's what we're looking at, phase changes. So we have phase changes such as melting or freezing. I'm going to put those together, right, because they're really opposite. And for water, that occurs at 0 degrees Celsius, right? Water freezes or it melts at 0 degrees Celsius. When we're talking about melting or freezing, two opposite processes, we're going to use something called the heat of fusion, delta HFUS. We're also going to be looking at phase changes like boiling and condensing. Again, opposite processes. You put energy in, it boils, you get energy out, it condenses. And in order to solve problems for this, we're going to be looking at the heat of vaporization. Great. What I would like to show you is how you would use a problem like this. And the other thing I want to tell you about both of these is that you need to add a sign. And what I mean is plus or negative, energy in or energy out. So I'm going to show you that via example. All right, so I'm going to do for you an example of melting. And here's the problem. 10 grams of a solid melts. What is Q? A couple of pieces of information I will provide for you. The molar mass of our solid is 100 grams per mole. And I will also tell you that the heat of fusion, and the reason I'm choosing heat of fusion is because it's melting, and so that's what I use, for this particular substance is 10 kilojoules per mole. So we're going to solve that problem. But here's what I want you to realize. This is a conversion. In other words, it helps us to convert between kilojoules and moles or moles and kilojoules. The other thing that you have to remember, and I mentioned this up here, is you need to add a sign. So melting, you have to put energy in to melt it. Energy in, remember, is endothermic, and so it's positive. So I am going to add a positive in front of the kilojoules per mole, so I know that's energy in. All right, if I can convert between kilojoules and moles, moles and kilojoules, and I have 10 grams, I know I can convert that into moles. So that's what I'm going to do. I have 10 grams at a molar mass of 100 grams per mole. And I know I need 10 kilojoules per mole. So mole will go on the bottom. My 10 kilojoules will go on the top. Moles cancel, grams cancel, and I am left with 1 kilojoule. In other words, I need to put in 1 kilojoule of energy to melt that solid. Notice there's no Q equals SM delta T in here. I just did a unit conversion. Do another example. Condensing. All right, here's an example. 10 grams of a liquid condenses. What is Q? Remember, what is heat flow? Once again, I'm going to tell you that the molar mass of my substance happens to be 100 grams per mole. But this time it's condensing. So with condensing, I use heat of vaporization. So I look up on a table somewhere the heat of vaporization of this substance, and the table reads 50 kilojoules per mole. But remember, I need to add a sign. So condensing, I have to ask myself, is that energy in or energy out? Well, boiling is energy in. Condensing is energy out. Energy out is negative, so I'm going to add a negative to that number. And then I can go ahead and actually do the calculation. So 10 grams of my liquid, I'm going to convert it to moles because my conversion is in kilojoules per mole. So 100 grams, 1 mole. I'm going to put mole on the bottom so it canceled, and kilojoules on the top. This is negative 50. And when I calculate that, I get negative 5 kilojoules. In other words, 5 kilojoules are given off when that liquid condenses. So that's the new part I'm going to add on, is when we have a phase change, we have to go back to unit analysis. Chemical reactions are going to have their own delta H called delta H of reaction. And we're going to treat it just like phase changes, but that's going to be coming up later. Okay, but it won't be too hard. It's just going to add just like phase changes. All right, so what I want to do is show you something and then just do some example problems to help you. I'm going to show you something called a heating curve. And with a heating curve, I'm going to specifically draw a heating curve for water. It's a graph. And I'm going to graph temperature versus time. And it's going to look something that is really, hold on, let me redraw that. That's supposed to end it. All right, we're just going to start over again. Wow, bad drawing. There we go. And this represents 0 degrees for water. This represents 100 degrees for water. So a couple things that are on this graph. Down here, when my water is below 0, it's a solid. In this region, when it's between 0 and 100, it's a liquid. And above 100, it's a gas. So I know this is a solid, this is a liquid, this is a gas. I also know that at 0, my solid melts, or if I go back the other way, my liquid freezes, right? And at 100, my water boils, or if I go back the other way, it condenses. So I have some things that happen. If I go this way, this is melting. If I go the other way, this is freezing. If I go this way, it's boiling. If I go this way, it's condensing. So based on what I told you, in this region, this is where you use the heat of fusion. And in this region, this is where you use the heat of vaporization. Great. The other thing I'm going to add is that, remember, melting is energy in. So melting means you use that number positive. Freezing, you have to get rid of energy. So you make that number negative. Boiling, you put energy in, so it's positive. Condensing is energy out, so it's negative. So that's what you would do for the signs for heat of fusion or heat of vaporization. All right. In these regions, you have temperature changes. You can have hot steam get hotter, so you could use SM delta T. Here you have liquid water. As long as it stays liquid water, if it starts as cold water and gets to warm water, you can use Q is equal to SM delta T. And same in this diagonal region. Q is equal to SM delta T. The specific heat capacity you memorized for water is this one. The specific heat capacity of liquid water. The specific heat capacity of gaseous water is different. The specific heat capacity of ice is different. I would give those to you, but this one you memorize. That's the 4.184 joules per gram degree Celsius. All right, heat of fusion of water. I don't think we're going to have you memorize this, but here's the numbers so that you don't have to look them Heat of fusion for water is 6.02 kilojoules per mole. The heat of vaporization for water is 40.6 kilojoules per mole. So that way you have them in a nice, neat spot. And one thing to remember with these numbers is you must add a sign, positive or negative. It's not built in. You have to decide what to do with it. All right. You guys are ready for just the two examples I want to do. So here's an example problem that you might encounter. So here's the question. How much heat is released when 100 grams of steam condenses to liquid water all at 100 degrees Celsius? So I have a mass of water. It's steam, so I know it's a gas. It's going to, a liquid, and I know the temperature. So in this little graph, and I often recommend drawing it just so that you can kind of keep track of where we were. What it's saying is you're starting with 100 grams of steam at 100 degrees. Well, at this point, this is when it's all a gas. At this point, it's liquid water. And along the line is when it boils, where they're both present. So I'm starting here. And I'm releasing it. I'm going to condense it. I'm going to cool the water off. And it's going to, oops, I went too far. It's not going to cool the water off. Yikes. I'm thinking ahead. It's going to condense it to right here. So it's not going to cool down. It's going to stay at 100. My apologies. So I'm starting at steam at 100. I'm going to liquid at 100. Since it's a phase change, I'm going to use my heat of vaporization. That's what I know, which I know for water is 40.6 kilojoules per mole, but I need to give it a sign. So going from condensing gas to liquid, the question is that energy in or energy out? It's energy out. That makes it negative. So I have to add that negative in. Please don't forget to do that. All right, so how do I do it? Well, that's my conversion from kilojoules to moles, moles to kilojoules, and I have 100 grams. So just like before, I'm going to take my 100 grams of water and I'm going to convert it to moles, 18.02 grams in a mole, and I've got negative 40.6 kilojoules given off for every mole. So when I compute that, I plunk it into my calculator, I get negative 225 kilojoules. So that's my answer. Oops, sorry about that. That's my answer. So I end up having 225 kilojoules given off when that happens. All right, last question. So here's the question. Let's actually scroll that up for you. How much heat is required? That's already telling me it's probably going to be positive, right? I got to put energy in to raise the temperature of 20 grams of ice at 0 degrees Celsius to steam at 100 degrees Celsius. I'm going to sketch this graph, and I would encourage you to do it all the time because it helps you to know what you're doing. So here's what this is saying. This is saying I have ice at 0. Well, here is where it's a solid. If I get to the other corner, this is where it's a liquid, and along the line is the phase change of melting. So I'm starting with ice at 0. I need to get it up to steam at 100. Well, here's the corner where it's steam at 100. So I actually need to first melt it. Then I'm going to have liquid water at 0, and I need to get that liquid water up to 100 degrees. So that's number 2. Then I need to boil the water. That's number 3. This is going to take 3 steps. to get there. All right, let's do each step in order. Number 1, I got to melt the ice. I know my heat of fusion is positive 6.02 kilojoules per mole. Hey, Mrs. May, how did you know it was positive? Because I'm putting energy in to melt it. So this is like my other problem. So I have 20 grams of ice, which is water. I'm going to convert it into moles. And I'm going to use my 6.02 kilojoules per mole. And when I compute that with 2 sig figs, I get 6.7 kilojoules. So that's this. Now I have liquid water at 0 and I need to heat it. So I'm in this region right here. Number 2, 0 degree water to 100 degree water. Well, that's a temperature change. So I'm going to use Q is equal to SM delta T. Okay, so 4.184 joules per gram degree Celsius times my mass of water, which is 20 grams, times my temperature change, 100 final, 0 initial, so 100 minus 0, that's a positive number. And when I solve for that, I get 8,368 joules. But I'm only allowed 2 significant digits, so 8,400 joules. So it takes that much energy to melt it and this much energy to raise the temperature to 100. And now I have one more step, step 3. So in step 3, I'm going to boil it. Well, the heat of vaporization for water is 40.6 kilojoules per mole. I need a sign for that. Energy in to boil it, so positive. And now I'm just going to do like what I did with melting, right? 20 grams of water, convert it into moles, 40.6 kilojoules per mole. And when I plunk that into my calculator, oops, I get 45 kilojoules. Well, now I have 3 answers. Well, that's because I need the energy it takes to melt it, heat it, and boil it, and I need to add them together. I noticed that 2 of the 3 are in kilojoules. This one's in joules, so I'm going to convert it into kilojoules to make my life simple. And so my Q is just going to be all of them added together. 6.7 kilojoules plus 8.4 kilojoules plus 45 kilojoules. I'm restricted now to the ones place. So when I do that, I get 60 kilojoules. That's how much energy it's going to take. All right, good job, you guys.